It is the 14th of March, 1945, and the morning air above the Möhne Dam in the Ruhr Valley trembles with an unfamiliar sound. German engineers working in the reinforced concrete bunker beneath the dam feel it first as a vibration, then as something far more terrifying, a compression of air that seems to come from everywhere and nowhere at once. They have heard the roar of bomber engines before. They have sheltered from conventional explosions countless times across 5 years of relentless warfare. But this is different. The sound arrives alone from a single aircraft. The explosion that follows does not concentrate itself in a single point, but rather ripples outward in waves, as though the earth itself has been struck by an impossibly large hammer. The massive dam, which had resisted thousands of tons of conventional bombs, begins to shift. Engineers watch, frozen in disbelief, as the structure they had reinforced with all the ingenuity of the Third Reich simply sinks. Water, held back by engineering excellence, begins to pour through a gap that should not exist. By the time the morning light fully breaks across the Ruhr, the valley floor below is a torrent of destruction. One aircraft had done what an entire air force had failed to accomplish. The weapon was unlike anything they had encountered, and the implications struck German military planners with the force of a thunderbolt. They did not yet know its name, but they would learn to fear it with an intensity that bordered on dread. This was the Grand Slam, a bomb so revolutionary in concept, so devastating in execution, that it would reshape the final months of the war and demonstrate that sometimes defeating an enemy required thinking, not like a soldier, but like a scientist armed with mathematics and an impossible dream. The problem that faced British bombing strategists throughout 1943 and 1944 was not a lack of ordnance or determination, but rather an abundance of German ingenuity in concrete. The industrial heartland of Nazi Germany, the Ruhr Valley, the Rhineland, the vast manufacturing complexes that fed the Wehrmacht, all lay protected beneath layers of reinforced concrete so thick that conventional bombing had become almost theatrical in its futility. The RAF had developed tremendous striking power. 4 engine bombers flew in formations numbering in the hundreds, each carrying tons of explosives. Entire cities had been reduced to rubble, and yet certain targets remained stubbornly intact. The massive dams that provided water and hydroelectric power to German industry seemed almost impervious. Deep bunkers protecting U-boat construction facilities shrugged off conventional bomb loads as though they were minor inconveniences. Precision bombing had proven more difficult than pre-war theorists had imagined, and area bombing, whilst devastating to civilian populations, could not always penetrate the hardened structures that mattered most militarily. By 1943, the situation was becoming strategically frustrating. Intelligence indicated that German heavy water production, essential for their atomic weapons program, was concentrated in facilities buried so deep and protected so thoroughly that no existing bomb could reliably destroy them. The Tirpitz, pride of the German Navy, lay in Norwegian fjords surrounded by such dense anti-torpedo netting and protected by such formidable defences that conventional approaches had failed repeatedly. Weight alone was not the answer. Engineers could always build thicker concrete, deeper bunkers, more elaborate protection systems. What was needed was not simply more explosive force, but an entirely new principle of destruction. The problem was not how to deliver more tons of TNT, but how to translate explosive energy into mechanical effects that concrete could not withstand. How could British science find a way to defeat engineering that seemed to exceed all reasonable expectations? The challenge appeared almost impossible, requiring the kind of breakthrough that comes only rarely in wartime, and only when someone brilliant enough refuses to accept that certain targets are invincible. That someone was Barnes Wallis, a designer whose earlier work on the bouncing bomb had already demonstrated an almost preternatural ability to bend physics to military purposes. Working at Vickers Armstrong with the full backing of Air Vice Marshal Ralph Cochrane and the support of the highest levels of British command, Wallis began to develop a concept that was radical, even by wartime standards. Whereas conventional bombs relied on detonation to create a shockwave that spread outward in all directions, Wallace theorized that a different approach could achieve far greater structural destruction. If a bomb could be designed to penetrate deep into the earth before detonating, the explosive force would be channeled downward and sideways, forcing the earth itself to heave and convulse. The shock wave, trapped beneath the surface, would transfer its energy through ground and rock with devastating efficiency, creating what amounts to a localized earthquake. The mathematics were complex but compelling. A 10-ton bomb detonating at ground level might crater the earth and destroy surface structures. But that same 10 tons of explosive detonated meters below the surface would lift and throw enormous quantities of earth and rock, destabilizing anything built upon it. The brilliance lay in understanding that structures built by humans, however strong, ultimately rest upon earth and stone, and if that foundation could be catastrophically disrupted, even the most robust engineering would fail. The Grand Slam bomb that emerged from this work was a monument to this principle. Standing nearly 4 meters tall and weighing 9,979 kilograms, just under 10 tons, it was by far the heaviest bomb in operational use by any air force at that time. American equivalents existed, but none approached either the elegance of the design or the specific tactical doctrine that had been developed to deploy it. The casing was fashioned from special alloy steel, hardened to withstand the stresses of the impact and to penetrate soil with minimal deformation. The nose was shaped to reduce air resistance and to cut through earth, rather than to tumble or bounce. Inside, the bomb contained 3,629 kilograms of explosive material, principally Torpex, a mixture that had been developed to provide greater destructive force than conventional TNT. The weapon was so heavy that it required a specially modified Lancaster bomber, stripped of most defensive armament and modified extensively to accommodate the load. The bomb bay had to be enlarged. The aircraft's structure was reinforced. Drop tests were conducted to ensure that the airframe could withstand the stresses of carrying and releasing such an enormous weight at operational altitudes and speeds. Manufacturing the Grand Slam proved to be an industrial challenge of considerable magnitude. The hardened steel casings had to be produced to exacting specifications. The explosive filling had to be manufactured with precision and then inserted into the casing with extraordinary care. A single manufacturing error could render a bomb useless or, far worse, cause catastrophic failure during loading or deployment. Production was concentrated at the Royal Ordnance Factory at Firth of Forth in Scotland, where craftsmen and engineers worked to construct these weapons. Estimates suggest that production reached roughly 80 Grand Slams per month at peak capacity, though exact figures remain classified in official records. Each bomb represented not just an engineering marvel, but an investment of resources, labor, and scientific expertise that only a wealthy and industrialized nation could sustain. The Lancaster bombers that would deliver them had to be modified at RAF maintenance depots, a process that required specialist engineers and weeks of work per aircraft. The operational debut of the Grand Slam came on 14th March 1945, when a single modified Lancaster, piloted by Wing Commander J.B. Tate, carried the bomb across the North Sea to attack the Bielefeld Viaduct, a massive railway bridge that the Germans had successfully protected through conventional bombing campaigns. The viaduct was crucial to German rail logistics in the final months of the war, and its destruction would significantly impede the movement of troops and supplies. At 0612 hours, at an altitude of approximately 2,743 meters, the bomb was released. The impact and subsequent detonation created a shock that lifted an entire section of the viaduct into the air and collapsed it with such violence that observers on the ground watched in stunned silence. One bomb had accomplished what numerous conventional raids had failed to achieve. Over the following weeks, Grand Slams were deployed against similar, heavily reinforced targets. The Arnsberg railway viaduct fell to the same tactic. The Ulm railway bridge collapsed. Specific accounts from German observers described the shock and incomprehension that greeted these attacks. Defense against conventional bombing had become almost routine. Anti-aircraft guns, fighter patrols, and shelter had developed into a predictable pattern. But there was no defense against the Grand Slam. No anti-aircraft gun could damage a bomb traveling at terminal velocity. No fighter could intercept a Lancaster moving at 240 knots at operational altitude. And no conventional bunker or shelter offered protection against a shock wave that arrived through the Earth itself. If you are finding this material as compelling as we do, a quick subscribe helps more than you know, and it allows us to continue exploring the extraordinary engineering achievements that shaped the Second World War. German attempts to match or counter the Grand Slam reveal much about the technological disparity that had opened between Britain and the Reich by 1945. The Germans possessed their own heavy bombs, certainly. The Fritz X guided bomb and the HS-293 missile represented genuine innovations in weaponry, but both had been developed with a different strategic purpose as anti-shipping weapons, and neither possessed the sheer destructive capacity of the Grand Slam. German designers had attempted to create a penetrating bomb of similar concept, the Düsenspreng bomb, or jet-propelled bomb, which was intended to combine the penetrating principle with powered flight to achieve greater accuracy. However, technical difficulties and the advancing Allied military situation meant that this weapon never entered operational service. More fundamentally, the Germans lacked the manufacturing capacity to produce weapons of the Grand Slam's size and precision. The Third Reich's armaments industry was, by 1945, laboring under constant bombardment, restricted fuel supplies, and the demands of multiple simultaneous weapons programs. The decision to develop a bomb of such enormous size represented a commitment of resources that the Germans, already stretched to the breaking point, simply could not match. American equivalents deserved serious consideration. The Americans had developed the Tall Boy, a 6,299-kilogram bomb designed by the British and manufactured under license in the United States. The Tall Boy preceded the Grand Slam and demonstrated many of the same principles of penetration. However, the Tall Boy lacked the sheer destructive force of the Grand Slam. Where the Tall Boy achieved penetration through streamlined design and weight, the Grand Slam added dramatically greater explosive content and a casing specifically hardened for Earth penetration. The mathematics of destruction are unambiguous. 9 tons of TNT equivalent detonating beneath the Earth creates a fundamentally different effect than 6 tons. The Grand Slam was not merely an incremental improvement, but a qualitative leap in destructive capability, and this distinction was apparent to every German engineer in general who witnessed its effects. The historical impact of the Grand Slam extends beyond the simple mathematics of how many bridges were destroyed or how many cubic meters of earth were displaced. Psychologically, the weapon affected German morale and strategic decision-making in the final months of the war. The appearance of a single Lancaster dropping a single bomb, with no possibility of interception or defense and no possibility of repair for the target, represented a form of technological defeat that was nearly absolute. German commanders found themselves unable to defend against something, and this knowledge eroded confidence in their ability to conduct sustained resistance. Additionally, the success of the Grand Slam influenced post-war thinking about precision weapons and the penetration principle. The Soviets and Americans both captured German and British technical documentation and examined captured bombs and bomb fragments with intense interest. The principle of using shaped charges, penetration, and delayed detonation became foundational to the development of bunker-busting munitions throughout the Cold War and beyond. Modern precision-guided munitions, particularly those designed to penetrate fortified structures, owe a direct intellectual debt to the Grand Slam's basic principles. The bomb demonstrated that sometimes the most effective weapon is not necessarily the most obvious one, and that scientific innovation could overcome engineering obstacles that seemed, at the moment, to be insurmountable. Today, surviving examples of the Grand Slam bomb can be examined at the RAF Museum at Hendon in London, where the sheer physical presence of the weapon, nearly 4 meters of hardened steel and explosive power, communicates something that statistics alone cannot convey. The public can stand before it and contemplate the moment when British scientists and engineers looked at a problem deemed unsolvable and refused to accept defeat. It is 14th March 1945 again, but now we see the wider context. The Bielefeld Viaduct had seemed invincible, not because of the height of its supporting pylons or the thickness of its spans, but because it had already survived so many attacks that German engineers had settled into a comfortable certainty that it would never fall. Certainty itself became the weakness. When the Grand Slam arrived, it did not demand that engineers defend the viaduct better or that they devise a clever countermeasure. It demanded something far more difficult, that they abandon their assumptions about how bombs worked and what was possible. The weapon carried within it a principle that transcended mere size or explosive force. It represented a moment when British science, facing a seemingly impossible challenge, had refused to think within conventional constraints. Barnes-Wallis had not asked how to make a bigger bomb. He had asked how to make a bomb work differently, how to harness physics in a way that had not been tried before. The answer he found was elegant, devastating, and ultimately transformative in its implications. The Grand Slam stands as a monument to a particular kind of wartime innovation, one that emerges not from desperation, but from intellectual confidence and access to sufficient resources to experiment, fail, and experiment again until a breakthrough emerges. It stands in stark contrast to much of German weapons development in the final years of the war, which was often driven by Hitler's demands for weapons of spectacular power rather than by careful analysis of actual military need. The Grand Slam was born from analysis. Air Vice Marshal Cochrane had identified specific targets that conventional means could not destroy. That specific problem was handed to Wallis, who subjected it to rigorous mathematical and physical analysis. The result was not a weapon of spectacular power in the conventional sense. The Grand Slam was not the largest bomb ever dropped, nor did it contain the most explosive material. Rather, it was a weapon designed to solve a specific problem with the greatest possible efficiency. In doing so, it solved the problem utterly and completely. Not a single viaduct attacked by the Grand Slam was successfully repaired and returned to service before the war ended. The psychological and strategic impact vastly exceeded what the simple tonnage figures might suggest. Here, then, was the true lesson, that sometimes defeating an enemy requires not simply more of what you have been doing, but rather a fundamental reconceptualization of the problem itself. The British bomb that terrified German engineers was terrifying, not because it was larger than what they had imagined, but because it demonstrated that their entire framework for understanding bomb design had been incomplete. And in that moment of realization lay the seeds of their defeat.